Extreme Physics.
Today, why don't we do kind of a virtual lab? I usually do this in class with real light bulbs and batteries and stuff like that, but that's not going to work today. So why don't you go to Phet, P-H-E-T, on the Googles, right? They'll take you to the Phet website, and this is from the University of Colorado. They got some great physics simulations here, and we want physics, and we're going to want electricity, magnets, and circuits. And why don't we go to Circuit Construction Kit DC Virtual Lab? All right, so there we go, and we'll launch that. All right, so you got your batteries, and you got your light bulbs, and today I'm gonna have you try and light up the light bulbs. Two ways. First, I want you to light them up in such a way that if I disconnect one of the light bulbs, the others stay lit. Now, when you connect these things, if you want to rotate this around, you just kind of grab it here. If you just want to move it across, you grab it up in the bulb part. But you're going to need wires. So here's a wire. I can connect one end to the battery and then another end to the bulb. And there we go, and it lights up. So what I want you to do is set up a circuit so both bulbs are lit like I have here. But if I disconnect one of them, the other is unaffected. It stays lit, and it stays lit as bright as it was initially. So I could disconnect either one of these, and we can see that the other stays lit. And all right, so why don't you give that a try? Two bulbs lit. When one goes out, the other stays lit.
Pause the video now.
All right. In your circuit in which one of the other bulb stayed lit even if the other was out, should have been something kind of like this, where basically one end of each bulb has a direct connection to the top of the battery. In this case, both my nubbies, they didn't both had to be nubbies, but they all had a direct connection to the top of the battery, and the other, in this case the side, was connected directly to the other end of the battery without having to go through anything else. In that way, if I disconnected a portion of it, wrong one, disconnected, boom, like that, you can see that we were still fully connected to the battery, and we still had a potential difference of whatever the battery voltage is across the bulb. This one didn't because it wasn't connected. But you'll notice that this bulb doesn't change. When I disconnect that, the flow through this bulb remains consistent. One thing does change, though. If you'll notice, the flow through the battery will increase when I connect this again, because these are equal light bulbs, and you can see that the flow through each one of them is the same, and when they come together, the flow doubles here, right? Because we have this flow coming into this junction, this flow coming into that junction. So we have twice as much flow here. We have twice as much flow through the battery when both bulbs are connected relative to just one. We see the flow through the battery has lessened because the only charge that is going through the battery now is the one that's going through the one light bulb. Now we got the flow through both light bulbs, so we've doubled the flow. This is called a parallel circuit. In a parallel circuit, all the devices are connected directly to the source of potential difference. They don't need to go through anything else. So why don't you try now to connect these in such a way so that if I disconnect one of the bulbs, the other one also disconnects.
Pause the video now.
So here's my circuit and it's connected. So if I disconnect one of them, they both go out. I disconnected this one and the other one went out. And I could do the same here. If I disconnect that one, this one goes out, right? All right, so you should have, in order to do that, you should have had a setup kind of like this. This is called a series connection. And one thing you'll notice is that there's only one path for the charge to flow. So if I break that path by either the bulb burning out or I disconnect the bulb, the path is disrupted. I don't have a closed circuit, so it can't maintain potential difference, and the flow of charge stops. You also notice these aren't as bright as they were before. When I had them connected before in parallel, like if I just disconnected this and connected this directly, you can see this is brighter. When I connect them like this, it's dimmer, and that should make sense because the voltage drops across here are going to be less. They're going to be split between two, right? For any closed loop, the sum of the voltage gains has to equal the sum of the voltage drops. Here's my voltage gain, and I have two drops. So whatever this voltage is, what is this? This is 9 volts, right? So there must be 4.5 volts dropped across each one of these. And in fact, why don't you set that up and measure it? Why don't you get out your voltmeter and measure the voltage drop across these right now?
Pause the video now.
All right, so I'm going to do it. This is a voltmeter. I need to put one probe on one side and the other probe on the other. And oh yeah, 4.5 volts. 4.5 volts. All right. And then, like they said, this is 9 volts. Boom. All right. Why don't you take a moment, too, while we're here, and why don't you measure the current? How much current is flowing in the circuit? We have 9 volt battery and 2 10-ohm light bulbs. Why don't you measure the current using your ammeter in this circuit?
Pause the video now.
Right, the ammeter is a little more difficult to deal with. We actually have to open the circuit up. I think I'll open it up right here. Boom. Got to open it up. This has to be in the circuit, and boom, 0.45 amps is the amount of current flowing in this circuit, right? All right, this is a series circuit. Now, you'll notice with a series circuit that neither of the connections is directly across the battery. This portion of the light bulb is to the top of the battery, but this one has to go through another component before it gets to the bottom. So this is not connected directly to the battery. Both sides aren't. Neither is this one. This side is connected directly to the battery, but the other side is connected to the other light bulb. So I do not have a direct connection to the battery with either one of these, and that's why when one goes out, the other goes out. So that is the nature of a series connection. This is a series circuit, one object after the other. Now, one thing we'll need to notice in a series circuit is the current is the same everywhere, right? There's only one path, so the current is the same everywhere in a series circuit. All right, let's take a look at our notes. Here we talked about the different types of circuits. First, we have a series circuit. And let's take a look at the current in a series circuit. In a series circuit, there is only one current path. The current is the same in all components, all right? So any water that flows through this water circuit has to go through each component and all the way around. It goes through everything. If it goes around back to the pump, it's gone through every component. One component is after the other. And therefore, the current must be the same everywhere and every throughout the circuit. Otherwise, you'd get a buildup of water, right? And the pipes would burst. So that doesn't occur. So the amount of flow has to be the same everywhere in this circuit because there's only one path. And here's our equivalent electrical circuit. We need a continuous path through each, in this case, light bulbs that goes through the filaments, goes around, and then back to the battery. And this is the way we would draw it with using our schematic symbols on the reference table. And here's our battery. Here's the positive side of the battery, and we have these connected to 3 different light bulbs, which we've labeled R1, R2, and R3. Right? So the current through the battery equals the current through bulb 1 equals the current through bulb 2 equals the current through bulb 3. Right? The current is the same everywhere in a series circuit. Now, the voltage, on the other hand, is not the same everywhere in a series circuit, as we've talked about earlier. In any closed loop in a circuit, the sum of the voltage gains, in this case, this is our V battery, it must equal the sum of the voltage drops. In this case, we have 3 voltage drops, so these drops, when added up, must equal the voltage across the battery. So the voltages are different throughout the circuit, right? Current's the same, but the energy per unit charge changes as you go around the circuit. And let's, boom. There's V1, there's V2, and V3. So the battery voltage must equal voltage drop 1 plus voltage drop 2 plus voltage drop 3, right? All right. Now, let's talk about this idea of equivalent resistance. The idea of equivalent resistance is that sometimes if you have a complicated circuit, it's easiest if you just completely simplify it. Instead of having a whole bunch of resistors or a whole bunch of loads, you just have one, right? And that would be called our equivalent load. Here's the idea. Here I have a circuit, battery connected to two light bulbs. It could be any load. It doesn't matter if it's a light bulb or whatever it is. And this is a 9-volt battery. And when I connect to these 2 light bulbs, 1.8 amperes travels through the battery. Now, the idea of an equivalent resistance is that we want to see if could we find a single light bulb or a single resistor that would behave like these 2 exactly, so the battery couldn't tell the difference. So basically, if I took this 9-volt battery and put it in this circuit, it would still draw 1.8 amps. It turns out that, let me get rid of this. If I were to take the same bulb, right, and connect it in a circuit like that, let's disconnect this battery. So we can see that the battery can tell the difference between this single bulb, which was exactly like these, and these 2 in parallel. It was drawing 1.8 amps with the 2 bulbs and only 0.9 here. Now, the idea is, can we find a bulb that would behave just like those 2 put together? And indeed we can. These were 10 ohm bulbs, and you'll see that if I drop this down to 5, right? Now, the battery can't tell the difference. It has a potential of 9 volts from top to bottom of the battery, and when connected to this load, it draws 1.8 amps, just like it did up here, right? When I put it up here, the battery can't tell the difference. It's still drawing 1. It doesn't know what's going on here. All it knows is how much current's going through it, and its voltage is 9 volts. So that's the idea of equivalent resistance. This bulb here, rated at 5 ohms, has the same equivalent resistance as 2 10-ohm bulbs connected in parallel. The battery can't tell the difference, right? So we say that this bulb here has an equivalent resistance to these 2 in parallel. All right, so that's the concept behind equivalent resistance. And this can be really useful for circuit analysis, doing these sorts of simulations. Sometimes we just want to know how much current is going through a load or a source of potential difference, And if we just knew the resistances of the loads and how they were connected, we could calculate how much current is going through there by using the concept of equivalent resistance. So for instance, we have a complicated circuit like this. We have 3 resistors, R1, R2, and R3, and we have a voltage source, and we have current flowing, and we want to replace this with a circuit with just one resistor, right? And this has to be chosen so the battery can't tell the difference between this one resistor or these 3 resistors connected in series. So that's the idea of equivalent resistance. This is going to be a much easier circuit to analyze than this one will be. So that's why we do it. It's to simplify things. So let's take a look at how we would figure out what the equivalent resistance is in a series circuit. All right, so I got a circuit right here, and it's got, we got 3 resistors and a battery, and they're in series. So the voltage across the battery equals V1 plus V2 plus V3, right? Sum of the voltage gains equals the sum of the voltage drops. But, and in this, the current's the same everywhere. So V1 equals IR1. V2 equals the current times resistance 2, and V3 equals the current times resistance 3. Just using this idea of that V equals IR, right? The basic relationship, I think, in your reference table. R equals V over I, right? So then you just solve that for V equals IR. Just doing a little algebra, right? So there we go. So V1 equals I1 R1, V2 equals I2 R2, V3 equals I3 R3. But since the current's the same everywhere, we can drop the subscripts on the I's because we don't need them. And so what I could do is just factor out the I's, and I got something like that. And I can, so I got, just solving for that, I equals V bat over R1 plus R2 plus R3. So therefore, those 3 resistors could be replaced by one equivalent resistance, where our equivalent in a series circuit is just the sum of the resistances of the elements in the circuit. Right? So for series, it's real easy. The resistances just add up, just like that. R equivalent equals R1 plus R2 plus R3. All right, and you can find that in your reference table. Regents reference table. So the current here, if I knew these resistances, I knew the voltage of the battery, I could calculate the current by just taking the battery voltage and dividing it by the equivalent resistance. And we're going to be doing that sort of thing quite often. So the battery can't tell the difference between those 3 resistors or that one resistance, right? So let's do a numeric example. We have a 24-volt battery, and it's connected in series with a 1 ohm, a 2 ohm, and a 3 ohm resistor. So I could replace this circuit with this circuit. So I could replace these 3 resistors with a single 6 ohm resistor because the equivalent resistance of these in series is 6 ohms. And I could calculate the current then through here by calculating the current here. So in this case, I got the current equals the voltage across this resistor, which is 24 volts, divided by the resistance, which is 6 ohms, and that equals 4 amps. Therefore, there must be 4 amps traveling through these wires too, right? So that's the idea of equivalent resistance, is that we could analyze the equivalent circuit and take information back. Since I know the current is the same everywhere in a series circuit, I could take that current information and bring it back to that circuit. All right, why don't we try a problem? We got equivalent resistance problem. 3 resistors, a 20, a 30, and a 40 ohm resistors are connected in series to an applied voltage of 120 volts. Draw the circuit, Calculate the equivalent resistance of the circuit, the current through each resistor, and the potential drop across each resistor. Why don't you give that a try right now?
Pause the video now.
Three resistors, 20, 30, and are connected in series. All right. So I have 3 resistors in series. I'm going to draw a battery. Oh, probably not a battery, 120 volts. I'm just going to draw it as a square. This is probably some sort of power supply. 120 volts. That doesn't sound like a battery. And we got 3 resistors in series. So they're all along the same path. So I'll draw it like that. 20 ohms, 30 ohms, and 40 ohms. Guess I could have seen that one coming. 40 ohms. Draw the circuit. Calculate the equivalent resistance of the circuit. All right, well, our equivalent in series is just R1 plus R2 plus R3. You know, when you take the exam, make sure you write that down. Otherwise, they can ding you for not writing out the equation. So 20 ohms. And substitution with the units. Plus 40 ohms is 90 ohms. 90 ohms. All right. All right, so it's 90 ohms. So I could, here's my equivalent circuit. I still got 120 volts. But now I only have 1 resistor. Right? And it's 90 ohms. This is our equivalent. All right, so I want to know the voltage drop across each one of these. Well, if I only knew the current, I could easily do it. Oh, I can over here. It's easy. It's easy. I can't do it here because I don't know the voltage drop across here. I don't know the voltage drop across here. And I don't know the voltage drop across here. I do know the voltage drop across here because this is connected directly to my sense of my source of potential difference. So I equals V over R. We only have 1 current, 1 voltage, and 1 resistance in this. So we got, well, I guess we got 2 volts. We got a voltage gain and a voltage drop. 120 volts divided by 90 ohms. Oh, what is that? 12 divided by 9. So we got 1.33 amps. All right, so looks like 1 1/3 amps. All right, so that is so that means that this has 1.33 amps because the power supply can't tell the difference between 190 ohm resistor and these 3. So it's going to put out 1.33 amps. And all right, so now I can find the potential drop. The voltage across the 20 ohm equals I across through the 20 ohm times the resistance of the 20 ohm, which of course is 1.33 amps. And the resistance of the 20 ohm resistor is 20 ohms. And the voltage across the 30 ohm resistor equals I30 R30, which is 1.33 amps. It is a series circuit. The current only has 1 path, so it's the same everywhere. 30 ohms. And V equals to 40 equals I40 R40 equals 1.33 amps times 40 ohms. All right. Do a little calculation. All right, I got 26.7 volts, 40 volts, 53.3 volts. Do those answers make sense? Why don't you check to make sure they make sense?
Pause the video now.
All right. Well, it makes sense if they add up to 120. Let's see, 53 plus 40. All right, got 120. 120 volts. There we go. 120 volts. They add up to 100. Okay, good. All right. So is this making sense? We had from here to here, 26.7 volt drop. From here to here, we had a 40 volt drop, and from here to here we had a 53.3 volt drop. All right. Well, same current through each one of them, and so I would expect the greatest potential dropped across here because there's the greatest resistance, and it does, and those are less than. All right. So those seem like reasonable answers. Very good. Let's take a look at the dignified circuit of eternal happiness. If you haven't done that yet, do it right now, and I'll do it, and you can check once you're done with what I did.
Pause the video now.
All right, here we go. Got the dignified circuit of eternal happiness. In this circuit, R3 has a value of 20 ohms. All right, whenever they give you information in a paragraph, get it on your schematic diagram. You want everything on your diagram so you can do your analysis. So R3 is 20 ohms. All right. What is the power dissipated in R3? All right, well, gosh, if only I knew the voltage across R3 or the current through R3, I'd be okay. But I don't know any of those things. But I bet I can figure it out. I think I'm going to find the voltage. The voltage drop is going to be, let's see, we got 12 volts, and we got 7, so all the voltage drops have to add up to 12. So it's looking like there is, from here to here, a 5 volt drop, right? 5 and 4 is 9, but yeah, it's 12. Okay, so that must be 5 volts there. So let's calculate the power across 3. P equals V squared over R. You can find that in your reference table. That's V3 over R3. All right. Make sure you have those subscripts in there because that's really important. It's not just any voltage and any resistance. It's got to be those. So 5 volts squared divided by 20 ohms. It's 25 divided by 21 and 5/20. 1.25. 1.25 watts. Is that right? 25. Yeah, I think that is. So the power is 1.25 watts, I think. What is the value of R1? R1. Okay. Well, you know what I think I'm going to do? Because if I only knew the current there, I could find R1. So what I'm going to do, I think, is find the current through R3, because I know the voltage and the resistance, so I can find the current. The current's going to be the same everywhere. So I know that I1 equals I3, right? I1 equals I3 because it's a series circuit, equals V3 over R3 equals 5 volts divided by 20 ohms. Is that 0.25 amps? Is that right? 250 milliamps. We got, in this circuit, we have 0.25 amps flowing. I'm going to write that down. We have 0.25 amps, but that's not what they want. You want to know what R1 is. Well, R1 equals V1 over I1 equals 3 volts divided by 0.25 amps, right? Is that 12 ohms? Let's see. I think it is. 12 ohms. R1 is 12 ohms. Oh, what's R2? All right. Well, that's easy. R2 equals V2 over I2. Current's the same everywhere. Voltage isn't. 4 volts divided by 0.25 amps. Let's see. Is that 16 ohms? 16 ohms right there. 16 ohms is R2. And what is the total power dissipated in the circuit? Well, the total power is going to be supplied by the battery, and it's going to be used up by the resistors. So I'm just going to calculate the power supplied by the battery. So the power total is going to be VI of the bat. 12 volts times a quarter of an amp, or 250 milliamps. So 12 divided by 4, I guess, is 3 watts. P total is 3 watts, I believe. That was the dignified circuit of eternal happiness. Let's take it down a notch. And we're going to try the shallow circuit of mournful pride.
Pause the video now.
All right, we're going to take it down a notch. We're going to do the shallow circuit of mournful pride. What does the ammeter read? Current! Actually, I get that on a test, and it's very sad when I have to take all the points off. Yes, of course it reads current. We want to know how much. What does the ammeter read? All right, so I got to find... Now, this is a series circuit, so I just need to find the current anywhere in the circuit. All right, I think I'll find it right there. I through the 10 ohm resistor equals voltage across the 10 ohm divided by the resistance of the 10 ohm resistor, and the voltage is 5 volts, and the resistance is 10 ohms. So I guess there's half an amp, or 500 milliamps traveling in that circuit. So that's what the ammeter reads right there. That ammeter reads that. If it was here, it would read the same thing. If it was here, it would read the same thing, and so forth. What is R3? R3 is a resistor. That's not what they want. They want to know the value. R3. All right. Well, okay, I think what I'm going to do is, because if I knew the voltage here, I'd be all set. So I need to know the voltage here. I can figure the voltage out here by, I know the current is half an amp, so let's find the voltage across the 20. V20 equals I20, R20. Well, the current through the 20 is the same as the current through everywhere. It's half an amp. And the resistance of the 20 ohm resistor is 20 ohms. So 20 times half, I guess that's 10 volts. All right. So it looks like we have a 10 volt drop from there to there. All right. We have a 10 volt drop and a 5 volt drop. This must also be 5 volts. I guess that's 10 ohms. So this must also be 5 volts, right? Because they have to add up to 20. Now, if that's 5 volts and that was 5 volts, same current, this must be 10 ohms. But let's calculate it anyways, because that's just a roaring good time. Plus, believe me, you need to practice. What were we saying? Oh, R3. R3 equals V3 over I3, which is 5 volts divided by half an amp, which is 10 ohms. All right. Well, we knew that. At least I knew that. 10 ohms. All right. There's the shallow circuit of mournful pride.
Extreme Physics.